Now, I mentioned a couple videos ago that while we're using the procedures to calculate intervals and significance tests for our sample proportions, it's not perfectly accurate. And there is actually an interesting solution to make answers a little bit more accurate, which is sometimes called the +4 estimate rule. And basically what you're doing is you're introducing a little bit of uncertainty to the formula, which actually makes your results a little bit more accurate. So let's look at the formula for what a +4 estimate says. But basically, instead of using p hat, instead of using your exact sample, what you want to do is you want to take your successes in your sample and add 2 to it. And then you take the number of your sample size and add 4 to it. And so what this does actually is it just slightly adjusts your fractions by, notice if you were to just do 2/4 by itself, that would be 1/2. But it's essentially adding in 2 successes and 4 total results. So basically you're throwing in 2 successes and 2 failures. And what this does is give you like a couple data points of 50-50 in there, because this is especially useful when the sample size is small. It means it's more likely to get off results. And when the data is especially skewed, it's kind of nice to put it more in the middle. And it's kind of harder to explain why this makes it more accurate. And it's sort of a mysterious process in some ways, but it does improve the accuracy of a test. And let's just take a quick peek at how you could actually do this. So example 1 revisited says, use the +4 estimate rule to calculate a more accurate confidence interval for this scenario. And here again, let me erase, it says p is equal to 23%. This doesn't make sense here. That would, be the claim of the population, but we had a sample in which, actually this was not example 1. Example 1, we had 170 out of 2673. So let me fix that. And so our p hat before was 170 divided by 2673. And that would be our p hat. So again, basically the idea here is if we wanted to use p with the tilde above it, which is starting to run out of symbols to use for stuff here, but this is just not important. We would have, well, 172 divided by 2677. We just increase them artificially by 2 and by 4. And this would give us a new proportion. And now we've increased it ever so slightly to 0.0643. And then essentially from here, we're going to do exactly the same math as from before. We would just use p hat or p tilde instead of p hat to do our math. So let's run it. So we'd have 0.064. And let's go ahead and use one more decimal, 6.0643 plus z star, which we had to be, we'll just assume all the other parameters were the same from example 1, 98% confidence interval with the standard error. And also this will change the standard error a little bit, so let's recalculate that. That would be 0.0643 times 1 minus 0.0643 divided by, and then you miss my square root around this. Oops, wrong button. Didn't mess it up again, apparently. Insert the square root. Okay, there we go. Oh boy, now I need to retype this in. I typed it in the wrong order and now it's all messed up. So we wanted the square root. I also need this in the square root. So again, trying to do my standard error here for replacing p hat with p tilde. And p tilde we obtained to be 0.0643. So I need to multiply that by 1 minus 0.0643. And all of this will be divided by the new n. And again, we've artificially increased that to 2677. And actually, if you look at the instructions, it actually says to not increase that, which is a little bit strange. So we'll leave it as it is. But anyways, it gives us a little bit of a different top of our confidence interval. And if we look at, well, what's the bottom of our confidence interval? It would be somewhere between 0.53% or 5.3% and 7.5% or 7.6%. So what you'll notice is it's not really all that different, obviously, because we're just very slightly adjusting percentages. But what this will actually do is it will slightly increase the top end and the bottom end. And this is because in actuality, it's a little bit more likely that it will be a higher percentage from the obtained than it will be lower, just because it will tend to be more towards the average 50-50 split than it would be. It's less likely to be an extreme percent than it is to be not extreme. And that's why adding 2/4 kind of normalizes it. You could do the same thing with adding 3/6 or 5/7 or 5/10 or whatever, and it would have a similar effect. And again, it's a little bit arbitrary, but it's kind of a neat little trick, I guess.